So this is our physical foundation of biochemistry. We are going to be using this portion of our first chapter to begin to talk about enzymes. We will be revisiting enzymes later on this semester. We'll be evaluating enzymes on an individual basis, but this will be kind of our foundation, our starting point. So in order to move forward, what you need to understand and appreciate is that organisms perform energy transductions to accomplish work to stay alive. So living organisms exist in a dynamic, steady state and are never at equilibrium with their surroundings. Their surroundings are likely very dynamic and changing, so they have to respond accordingly. Now, another thing that's important is that energy coupling is something that you will, if you take metabolism, you will get into energy coupling quite a bit because you'll be talking about multiple processes taking place and the energy associated with those processes, how they are paired up to become energetically favorable. Biological catalysts reduce energy requirements for reactions while offering extreme or high specificity. We'll talk about enzymes and talk about models for how an enzyme selects a substrate later on this semester. And then finally, as the entropy of the universe increases, creating and maintaining order requires work and energy. So as the kind of surroundings change, well, an organism is going to have to respond to those changes and either change or do something to maintain. All right. So one of the most important discussions in biochemistry when it comes to a chemical reaction is the discussion of enzymes. Enzymes are your biological catalysts. Now, historically, prior to taking a biochemistry course, you probably have a little bit of an understanding of how to speed up a reaction. Two ways are the first two that are listed here. One, you can increase the temperature. What does the increase in temperature do? Well, it increases the number of collisions, potentially, or not potentially, but more than likely what it's going to also do is going to destabilize some of the molecules that are involved in the reaction. Our second way that you can speed up a reaction is by increasing the concentration of the reactants. So you provide more of the starting material, you're going to get more of the product at a faster rate. Now, items 3 and 4 on this list. These are the ones that are a bit more relevant to the study of biochemistry. This third item on the list is changing the reaction by coupling it to a fast one. The way that I think about that is I think about that in the context of a biological pathway. Biological pathways, you can break some of the individual reactions down and say, well, this reaction is slow, or this reaction requires a huge amount of energy, this other reaction requires a large amount of energy. When you pair those together, which we will talk about one of those in just a little while, the overall of the two reactions, so the combination of those two reactions is overall fast. And energy coupling is something that is regularly done in biological pathways. Now the fourth item there, lowering activation barrier by catalysis, well, that's something that's relevant to what you've previously studied with respect to an inorganic catalyst, but what makes this different, or what makes this discussion different, is we're not talking about a biological catalyst. We're not talking about an inorganic catalyst, we're talking about a biological catalyst. We're talking about an enzyme. Enzymes lower the activation barrier of specific reactions. So what we can do whenever we're discussing an enzymatic reaction, or any reaction for that matter, is we can look at an equilibrium constant and the Gibbs free energy to evaluate whether or not a reaction is going to be spontaneous or not. So if we use this equation right here, our coefficient lowercase a, reactant A plus BB yields CC and DD, that's at equilibrium, we can develop an equilibrium constant, or KEQ, which is the concentration of our products to their not prefix, our coefficient power divided by our reactants to concentration. And we can look at that as delta G naught is equal to negative RT ln KEQ. So we can look at and evaluate whether or not a reaction is spontaneous based on this information. So what we'll do in this class, and going beyond just this class to a biochemistry 2 or a metabolism class, is we'll talk about whether or not a reaction is favorable or the synthesis of a product is favorable. And so synthesis of complex molecules generally is going to require energy input and therefore is considered to be endergonic. That can be for a variety of reasons. For instance, the reaction might be thermodynamically unfavorable, in which case your delta G naught is going to be a positive number. The metabolic reaction might have too high of an energy barrier, in which case you'd see that displayed as this delta G double dagger is greater than 0 and therefore is a positive number. Now, the breakdown of some metabolites, on the other hand, is going to release a significant amount of energy and therefore is an exergonic reaction. So metabolites like ATP, NADH, and NADPH can be synthesized using the energy from sunlight and fuels. Cellular concentration of those is going to be far higher than their equilibrium concentration. Now these molecules, just as you can, as sunlight or something can be used to synthesize those in a photosynthetic organism, they can be utilized for breaking down, or sorry, you can take that energy to, well, convert it into a different form. So thermodynamics, delta G equals delta H minus T delta S. This is something that you can take back to your general chemistry 2 class. And what this amounts to is we can look at a process as being spontaneous when the delta G is less than 0. Therefore, it is a negative number. Now, delta H, on the other hand, well, what is that? That's the heat of your reaction. How is this actually going to be measured? And what is delta S? And how is delta S measured? So it's kind of easy to reflect and just kind of hang your hat on, well, I know that delta G is going to be positive or negative, therefore it's a spontaneous or a non-spontaneous process. But what about everything else within this equation? So we're going to go into those just a little bit. So the first variable in the Gibbs free energy equation that I want to talk about is enthalpy change, delta H, the heat of a reaction. And you can look at this as heat being released or absorbed. So I always think about this as the sodium hydroxide, solid sodium hydroxide, and water added to that. If you hold that in your hand and you don't have like an insulated container, what that's going to do is that's going to get warmer. That's heat going to be released. And that would be an example of an exothermic reaction, in which case the delta H value for that would be a negative value. On the contrary, on the opposite end of that spectrum, if you talk about adding urea to water, well, that is going to be absorbing heat. So if you think about that same thing where you're holding that container or that beaker in your hand where that reaction is taking place, well, that's going to seem to get cooler because what that is doing is it's drawing heat from your hand. So your palm is going to get cooler. Now, if delta H is 0, well, it's 0. It's not endothermic nor exothermic. So in general, exothermic reactions are going to be considered favorable, but some endothermic reactions are going to be spontaneous. Now, how is that taking place? Well, keep in mind, this is all about all of the variables of the Gibbs free energy equation. Next up, entropy change, delta S. That's all about order or disorder. Now, to put this into perspective, when you have a delta S that is negative, that means disorder is going down. So the system is becoming more ordered. Now, what we know is that the universe is ever expanding, so our delta S is going to be positive when a system is increasing in disorder. And that always sounds kind of awkward to me. It's increasing in disorder, order being something that I always have a tendency to think about things as being, is this desirable or undesirable? But it's important to just think about these things as, is disorder taking place is disorder increasing? If disorder is increasing, that means the system is becoming less ordered, therefore your delta S is a positive number. And the opposite, if the system is becoming more ordered, then your delta S is a negative value. Now, finally, what we've already kind of talked about was delta G. Now, if our delta G value is negative, then that is considered an exergonic and a spontaneous reaction, or a favorable reaction. If delta G is positive, that is an endergonic example of a reaction, and that would be an unfavorable reaction. So it's important to think about enthalpy change and entropy change and put it in the context of the Gibbs free energy equation. Delta G equals delta H minus T delta S. So keeping in mind those kind of criteria and those definitions, those examples that we thought about, let's look at how a reaction basically shakes out as being spontaneous or non-spontaneous. So what this table shows is comparisons of delta H and delta S. We're not looking at specific numbers, but we're looking at numbers as positive or negative. So let's look at this first example. We have a delta H value that is negative. Now that would be a reaction that is exothermic, and it's going to release heat, but also what's going to happen from an entropy perspective is that this reaction is going to lead to an increase in disorder. So this is a reaction that is going to be spontaneous. So it's going to be spontaneous at all temperatures. Now, I would recommend being familiar with and keeping pace with these values, these negative or positive values for entropy and enthalpy, rather than trying to plug a number in. So, trying to think about a temperature or something like that, because that's where you kind of get mixed up. Now, so this first example is entropically and enthalpically favored. So it's overall a spontaneous reaction. Now this next example, which I'm using my trackpad here rather than my, oh, no, I was trying to draw number 2, trackpad on my mouse, or trackpad on my laptop. So our second example here, we've got a system that is releasing heat, indicated by our delta H that is negative. Now what does our delta S say? Our delta S says that the system became more ordered. Okay, so is this a spontaneous reaction or a non-spontaneous reaction? Now, if you think about it from an enthalpy perspective, spontaneous, or it's almost like that's a vote for spontaneity. Entropically, it became more ordered, so that's a vote against spontaneity. But we have to reconcile those values. And the way that we reconcile them is we have to look at, well, what's the value of our temperature? Now, what you can conclude about the temperature and spontaneity or non-spontaneity is this is a spontaneous reaction only at temperatures below T equals delta H over delta S. So if you were to plug in these specific values, those number values, numerical values for delta H and delta S, that would give you a temperature at which, so long as your temperature were below that, then the reaction would be spontaneous. If it were equal to that temperature or above that, well, that would not be a spontaneous reaction. So think about this as this is going to be favorable at lower temperatures. Now that the term lower implies like something relative to something else, and this would be that standard. But if you wanted to kind of simplistically classify it, the second example, when delta H and delta S are both negative, probably at a lower temperature. I hope that makes sense. Now, our third example. Now I'm going to try to draw a 3 again. That's not horrible. It's not great, but nevertheless. Delta H is positive. Therefore, it's an endothermic reaction. So you have to put energy into this reaction. So think about where that energy could come from. Well, the environment. Okay. Entropically. So entropically, this is favored because of the fact that, well, it's leading to more disorder. So we've got 1 vote against spontaneity, and that would be our delta H because delta H is positive. 1 vote for spontaneity, and that's our entropy vote. So you've got to put energy into it, but the output is going to become less ordered. So that's good, that's good, that's good. Okay, now what this says is it's spontaneous only at temperatures above T equals delta H over delta S. Okay, so essentially the way that you could look at this is almost the opposite of our previous example. The reaction is enthalpically favored when delta H is negative. It's enthalpically opposed when delta H is positive. It's going to be entropically opposed when delta S is negative, but it's entropically favored when delta S is positive. Okay, so just as for example 2, or kind of category 2 right here, we said at lower temperatures, this one says at higher temperatures, which take a moment and think about that. This reaction is going to take place if energy is input. Well, if the environment provides that heat energy for that reaction, well, then maybe that's kind of enough. So if you did this at very high condition or very high temperature conditions, maybe that reaction is going to take place without a problem. Okay, now our last example. 4 should be an easier number to draw because it's lots of straight lines. There we go. Look at that. That's a 4 drawn like a champ. Okay, here we've got a delta H that is positive. So you got to put energy into that reaction. So thumbs up, thumbs down. Thumbs down. You got to put energy into that. Now, delta S is negative, meaning the system becomes more ordered. That's a vote down. So you've got 2 votes against spontaneity, against it happening without any outside influence. So let's look at our conclusion there. It is spontaneous non-spontaneous at all temperatures. Okay, does that make sense? We've got 2 votes against spontaneity, the system's becoming more ordered, bad news, and you have to put energy into it. So this is going to be non-spontaneous at all temperatures. All right, I hope that helps.